Computer Science 461, Software Testing Techniques. This is part 2 of our discussion on testing, and this presentation covers more of Chapter 8 of Somerville, but I also bring in some material from Pressman and from professional software testing organizations. So there's a bit of variety to the materials and opinions, and it's good to learn from multiple sources and to get information from multiple sources, particularly on some of these more advanced topics in computer science. So once your source code has been generated and you've got a working product, you need to test the software to uncover and fix as many errors as possible before you deliver it to the customer. So the goal of testing is actually to find errors. Now, you really can't do exhaustive testing, and Roger Pressman talks about a 100-line C program with 2 nested loops that executes from 1 to 20 times each on the loops, depending on the input conditions. Inside the interior loop, there are 4 if-else control structures. And Pressman estimates there would be 10 to the 14th different paths that could be executed by this program. So it's really impossible to exhaustively test it. He speculates that if you had a magic test processor, develop the test case, execute it, and evaluate the results in 1 millisecond, it would take about 3,170 years to completely test that program. And that's just for 100 lines of source code. So it can be quite complicated to completely exhaustively test software. So when testing software, you want to look for something called testability. And this is how easily software can be tested. So some characteristics of testable software. One is operability. The better it works, the more easily it can be tested. Fewer bugs block the operation. Observability. You can see the system state variables and operations. Those are all visible. Controllability. Software states and variables can be controlled by the test engineer, so you have control over it when you're testing it. Simplicity. If there's less to test, it's better. Stability. Infrequent changes to the software, so you don't have to rerun the tests. So it's not continuously being evolved as you're testing it. You're not trying to hit a moving target. And understandability. The better the documentation, the easier it is to design, execute, and evaluate tests to see whether it's performing according to specification. 2 broad types of testing are white box and black box. In white box testing, you can guarantee that all independent paths of the module have been executed at least once. And so white box is the philosophy that uses component level design to derive test cases, and it assumes that you know the structure of the code. You can exercise all logical decisions on their true-false sides, exercise all loops at their boundaries, and exercise internal data structures to ensure their validity. White box testing is usually performed earlier in the process than black box testing, which focuses on the functional requirements of the software. Black box testing attempts to find errors in the following categories: incorrect or missing functions, interface errors, errors in data structures or external database access, behavioral or performance errors, and initialization and termination errors. And it usually takes place later in the testing process. So the IEEE definition of a test case is documentation specifying inputs, predicted results, and a set of execution conditions for an individual test type. So for test case design, this is a part of the system in component testing where you create the test cases. And the goal here is to create a set of test cases that are effective in discovering the program defects. Again, the purpose of testing is to uncover any defects that are actually in the software. Components for a test case: you need inputs, outputs, and ranges, and some way to design an automated check if that's possible. So what makes a good test case? One that has a high probability of finding an error. One that is not redundant. You do want a little bit of redundancy, but you don't want to keep repeating the same test over and over again, especially if it's going to give you the same results. Best of breed. Basically, the test that has the highest likelihood of uncovering a whole class of errors is the one that you should use. And you don't want them to be too simple or too complex. In general, you want each test to be executed separately, and you don't want them to bleed into one another. So here's an example. This is taken from Utest. It's hard to see, but when you do a close-up, it looks eerily similar to what you had to do in CS 150 and 151. So the components of this test case are test case name, a description which explains the function under test, clearly state exactly what attribute is under test and under what conditions, the prerequisites. Every test needs to follow a sequence of actions which lead to the function under test, steps that you take to execute the test, input, what inputs are going to be used on the particular test, or if it's a lot of data, to point to the file where that data is stored, expected result, what should happen, the actual result, what actually happened, and then a status, pass or fail. And you can see here they do it in two environments, A and B, comments, and any references. As they say on Utest, it's a huge task to write effective cases with all the appropriate details. Once the test case documents are ready to be executed against it, it's typically only the beginning of the test effort. As you become more familiar with the application and become better in tune with the end user's perspective, you'll likely add more relevant tests. So again, this is something that we see over and over again in software engineering, is that things continuously evolve. So a couple of approaches to test case design. One is requirements-based testing, where test cases are designed to test the system requirements. Partition testing, identify input and output partitions, and design tests so that the system executes inputs from all the partitions and generates outputs in all the partitions. Structural testing, design tests that exercise all the different parts of the program. So requirements-based testing, basically you're exercising the requirements that you developed in the requirement document. So each requirement has more than one test associated with it. It's good to make your requirements testable in the beginning when you wrote them, so it's easier to do the requirements-based testing. Partition testing, you have your input data and output results, and these usually fall into a number of different classes that have common characteristics. Because of this equivalent behavior, these classes are often called equivalence partitions or domains. So for example, all the positive integers would form an equivalence class. All the negative integers would form an equivalence class, and 0 might form its own equivalence class. You need partitions for the equivalent inputs and outputs, and what you want to do is you want to try to identify boundary values, things where the behavior of the system changes. For example, at 0 or at 1 or -1. Basically, wherever the system changes, those are going to be the boundary values. And you also want to do the midpoints. So for example, if you run a loop 0 to 20 times, you want to test the loop when it runs 0 times, 1 when it ran about 9 or 10, and 1 when it ran 20. So especially when you're testing sequences, arrays, and lists, basically you want to use different sequences of different sizes, test the first, middle, and last elements as they're accessed. So here's an example with binary search, and here are the equivalence partitions. Elements that are, you're looking for an element that's lower than the midpoint, an element that's lower than the, or higher than the midpoint, and an element that occurs precisely at the midpoint. And so here you can see what a set of test cases for doing binary search would look like. You have a sequence with a single value and the element is in the sequence, a single value not in the sequence, more than one value with first element, last element, middle element, and not in the sequence. And then you can generate a set of test data that you could run this on. That one's taken from Somerville. And so here's what the actual test cases would look like. Here's your input array, what you're looking for, and then what output you can expect. You'd have another column that would indicate what output you actually got, and then the software developer could fix that function if there were any problems with it. Again, the partition testing is not exhaustive. Some equivalence partitions may not have been identified. You could have made errors in the partition identification, and you could have made errors with the test data. They could have been improperly prepared. Structural testing is an approach to test case design where the tests are derived from knowledge of the software structure, very similar to the Whitebox testing, in that you need to know the underlying structure of the algorithm and the code. There is an example in the book with binary search. And path testing is an example of structural testing where the objective is to exercise every independent execution path through a component or a program. It doesn't test all possible paths through the program, it just says we're going to do each one at least once. So each independent path is exercised at least once. And what you need to do this is a program flow graph where the nodes are decisions and the edges represent the flow of control. So for example, here is a flow graph for binary search, and you can see the decision point where we check the element and see if our midpoint is equal to what we're searching for, and you can see a branch between the midpoint is greater than the key or it's less than the key. And also if it's equal to the key, then we proceed to step 8. But you can see the flow graph structure of binary search. And once you have this flow graph, you can compute something called the cyclomatic complexity. And the cyclomatic complexity gives you an idea of how difficult it is going to be to test these things. Developed by McCabe in 1976, and you translate the program design to a flow graph. And then the number of regions in the flow graph correspond to the cyclomatic complexity. For a flow graph G, the cyclomatic complexity is edges minus nodes plus 2, or it's equal to p plus 1, where p is the number of predicate nodes in the flow graph. The edges minus nodes plus 2 is probably the simplest to use. So let's take a look at an example. So here we take the code over on the right, we translate it into the program flow graph on the left, and then we can count up the edges. There are 11 of them here, and there are 9 nodes that are in this graph. So the cyclomatic complexity of it is 11 minus 9 plus 2, which is equal to 4. So those are the general testing strategies. Now there are some specialized testing types that do take place in software engineering. Let's take a look at a few of those. The first is graphical user interface testing. So you can develop test cases that can that are based upon the behavioral model of the user interface. So how do users actually use the software? And then you can use automated testing tools to stress the functions that the users use most frequently. You can also set up a fairly sophisticated usability lab like we talked about in CS 340. For real-time systems, again, some specialized testing is required. Task testing, where you test each task independently. Behavioral testing, where you use techniques similar to equivalence partitioning of the external event models, and you create these via automatic tools. And then testing the full system, handling things such as interrupts, test cases based on the state model and the control specification. So there are some automated test tools out there, and testing is a pretty expensive and often tedious process. If you've ever tested a piece of software according to a test plan, you know how tedious it is, and it's not fun. A lot of people want to become video game testers until they realize how tedious it is to actually test the video game according to the test plans. So there are a lot of test tools that will automate things. Two broad categories are static testing. These are code-based testing tools, specialized testing languages, and requirement-based testing tools. The code-based testing tools accept source code as an input and perform a number of analyses on it that result in the generation of test cases. Specialized testing languages enable a software engineer to write detailed specifications that describe each test case and the logistics for its execution. And requirement-based testing tools isolate the specific user requirements and suggest test cases or classes of test that will exercise the requirement. For the dynamic tools, they interact with an executing program. They check path coverage, test assertions about the value of specific variables, and otherwise instrument the execution flow of the code. So you can also put these tools together into a Workbench. Typically you'll have a test manager, test data generator, an oracle that will make predictions about what the result should be, a way to compare files to see if the output is what you were expecting the output to be, report generator, dynamic analyzer, and a simulator. So a couple of professional tools, and this is by no means an endorsement of any of these tools. One of these is McCabe IQ, which is named for the guy who invented the Cyclomatic Complexity. This is his company, and it objectively measures software quality through advanced stack analysis and helps you visualize the architecture and highlights the most complex areas of the code base to identify bugs and to secure vulnerabilities. They also have a configuration management tool. Another example of a professional testing tool is Tvec, and basically this is a functional test generation system that automates the manual and error-prone testing activities, including test generation, test driver generation. Actually, they have a whole suite of tools that are shown on the next slide, and you can see the V there. They actually have a requirements management, a stateflow design tool, and they actually have things that will check for requirement defects or things that will test the state flow and simulate the operation of the system. And last but not least, one that we talked about in CS394 last semester, which is Utest, and that's a crowdsourcing platform for software testing. You can sign up to be a tester, or you can contract to have your software tested here. They have training for software testers and a large directory of software tools that can be found under tools.utest.com. As a final thought, Edgar Dijkstra once said, testing can only reveal the presence of bugs, not their absence. So there's no way to be sure that you're completely 100% error-free through testing. And I'll leave you with that final thought.